Okay, so hello and welcome back. So in this video we want to talk about the current divider circuit. Basically the current divider circuit is usually or normally built with two parallel resistors, meaning that you have a power supply over here, and it's connected to such resistors connected in parallel. Okay, and then these resistors go back to the power supply. So that is basically how this thing is built. So here you have your V of S, here you have, for example, your R1, here you have your R2, and basically your I of T is going through your circuit over here, and then once the current hits this point, it goes through basically it's split into two branches, basically I1 for example and I2, and then I1 goes through R1 and I2 goes through R2, and then here you have basically I2, here you have I1, and then when they will come together, and at this point they will basically be summed together or added together, and then you will have basically again I of T. So I of T is split here at this point into I of 1 and I of 2. I of 1 and I of 2 goes through the respective branches, and then at the end of those two branches they will be basically added back together to get I of T, and then again the same thing happens over and over again. So yeah, this is equal to I1. Now there is a couple of questions here. It says that which of the following relationships are valid for this circuit. So one of the relationships is, for example, V of S is equal to R1 I1. So of course the voltage across this resistor is going to be, that V is equal to I times R. So the voltage that is across this resistor is the product of the resistance of this resistor times the current going through this resistor. And as basically you see that your power supply is just connected to these two resistors, meaning that the voltage across R1 or V of R1 is equal to the power supply voltage V of S. V of R2 is again the same thing, V of S. So you can say that V of R1 is equal to V of R2, which is equal to V of S. So what that means is that basically then, and of course you know that the voltage across this resistor is equal to the current going through the resistor times the resistance of the resistor, which means that R1 times I1 is the same thing as R2 times I2 is equal to V of S. Okay, so And then you can of course write another relationship here, which is I1 to I2 is equal to R2 to R1. I1 to I2. So I1 over here is the same thing as, you know, that basically based on this relationship, I is the same thing as V to R. So V is the same for both of these resistors. So then I can write basically for this resistor, I can write so basically I1 so I can basically rearrange this formula or this relationship as well, and for example divide by I2. For example, over here I have R1. I1 is the same thing as R2 I2, and so if I divide by I2, for example, I will get R1 I1 divided by, for example, I2 is equal to R2 I2 divided by I2, and that means that basically I2 and I2 cancels out. You have R1 times I1 divided by I2 is equal to R2. And then if I divide by R1 again, both sides of the equation, I get R1 I1 over R1 I2 is the same thing as R2 divided by R1. And then these two will cancel out, and so then you will get I1 to I2 is equal to R2 to R1. Okay, so that's another relationship that you can get here. So the I2 to I1 is equal to R1 to R2. I1 to I2. I1 to I2 is equal to R2 to R1. Is equal to R2 to R1. Now, of course, you can take the reciprocal of both sides of this equation. You can write that as I2, for example, to I1 is equal to, for example, R1 to R2. You can write it that way as well, taking the reciprocal of both sides of this equation. It's basically only simple algebra, nothing more than that. So there is a procedure here that says that when you want to, when solving current divider problems, when solving current divider problems, what you need to do is that set up the ratio of the resistors and currents. Number one, set up the ratio of resistors and currents, which is basically, for example, I2 to, for example, you can write I1 to I2, and on the other side you'll get R2 to R1. You get R2 to R1. If you write it the other way around, you can write it, for example, I2 to I1 is equal to basically R1 to R2. Anyway, I mean, either way, that's basically the same thing. Now, once you set up the ratios of the currents and the resistors, you can rearrange the ratio to give you either I1 or I2 in terms of the other three variables, meaning that, for example, you can cross multiply here, and you can write this as I1 times R1 is equal to I2 times, for example, R2. And then, for example, if you want to calculate I1 over here, you can write I1 is equal to, for example, this whole thing, I2 times, for example, R2 divided by R1. Divided by R1. If you want to, for example, calculate I2 over here, you will get I2 is equal to basically this whole expression, I1 times R1 over R2, for example. I2 is equal to I1 times R1 over R2, for example. Or if you want to, for example, get R1, for example, you want to calculate R1. So R1 would be equal to this whole expression, I2 times, for example, R2 divided by I1. This is all just only simple algebra, meaning that if you have A times B is equal to, for example, C times D, to calculate to solve for A, you would write this as, you can write this as A is equal to C times D divided by B. Solve for B, for example, you would get B is equal to, again, this whole expression, C times D divided by A, for example. You want to solve, for example, for C, C would be equal to A times B, for example, divided by D. And solving for D, you would get basically A times B divided by C, for example, something like that. Okay. And of course, in these current divider circuits, you know that, I mean, apart from the fact that, you know, basically your circuit is always something like this. You have these two basically parallel resistors, and they are connected to some sort of power supply. This is your VOS power supply. Let's say that this is your R1, this is your R2, this is your I1, for example, this is your I2, and this is your I of t. And the relationship that we found was that, for example, I1 to I2 is equal to R2 is equal to I1 to I2 is equal to R2 to R1. Okay, so that was one relationship, and then based on that you can calculate what is I1, what is I2, what is R2, what is R1. Those four things you can calculate from this relationship. And also you know that basically I of t is equal to I1 plus I2. I1 plus I2. So that way you can calculate everything in these circuits. And we will of course do a couple of examples here. Okay, so now let's solve a problem over here, which is the values of two resistors in parallel and the total current flowing through the circuit are shown in this figure. What is the current through each individual resistor? Okay, so we have this circuit over here, which is basically some resistor over here and another resistor over here. The two resistors are connected in parallel, and over here you have I of t is equal to 2 amp, and then this is R1, which is equal to 2 ohm, and this is your R2, which is equal to 1 ohm. So this is basically I1, and this is I2. You want to find basically I1 and I2. So we said that I2 to I1, for example, is equal to R1 to R2. So then in this circuit, I can basically express right now, basically R1 to R2 is a ratio that I already have. It's 2 ohm and 1 ohm, so the ratio would be 2 to 1, which is basically 2 over here. But I2 and I1 are basically unknown, so that way I cannot solve this equation. What I can do is that I know that I of t, which is equal to 2 amp, is equal to I1 plus I2, because this is a parallel circuit. So that means that I of t is equal to, well, I1 plus I2, and so I can write this as I of t, I can write it as I can write it in terms of I2, for example. I of t, I can write it as or let me write it this way. I can write basically I of 2, for example. So I of 2 is equal to I of t minus I of 1. So then I of 2 is equal to I of t, which is equal to 2 amps, 2 minus I1. And then I1 is basically this thing over here. So I can rewrite this equation as basically I2, which is basically 2 minus I1 over I1 is equal to R1 to R2, which is 2 to 1, which is basically a 2. So then you can write 2 minus I1 is equal to 2 times I1, and 2 is equal to 2 times I1 plus I1, and 2 is equal to 3 times I1, and I1 is equal to 2/3 amps. 2/3 amps. And we said that I1 plus I2 is equal to I of t. So now this is I1 actually. Sorry. This is I of 1. So I of 1 is equal to 2/3 amps. So I write over here 2/3 plus I2 is equal to I of t, which is 2 amps. So I of t, I of 2 is equal to 2 minus 2/3. 2 minus 2/3, which is equal to 3, and 6 minus 2, which is equal to 4/3 amps. So I of 1 is equal to 2/3 amps, and I of 2 is equal to 4/3 amps. And if you add these together, you will get 6/3, which is equal to 2 amps. Or suppose that, let me do another example over here. Okay, so now suppose that your I of t, basically in all of these 3 examples, and I mean there are actually 2 examples. In all of these 2 examples, basically you have a resistor over here, and you have another resistor over here, and they are connected in parallel. There is some I of t coming in here. There is your R1, there is your R2. This would be your I1. This would be your I2. And that is basically your circuit. And basically I of t is given and the value of R1 and R2 are also given, and then you're supposed to calculate I1 and I2. That's basically the situation here. So now suppose that, for example, I of t is equal to 30 milliamps, and R1 is equal to 12 kilo ohm, and R2 is equal to 6 kilo ohm. Okay, so now suppose that your I of t is equal to 30 milliamp, and these are the resistors that you have. So the values of these resistors are in kilo ohm, and the value of the current is in milliamp. So they kind of go together, meaning that if you have basically V is equal to I times R basically, and if your voltage is in volts basically, if your current is in milliamps, if you multiply it by some kilo ohm, then kilo and milli will cancel out, and then you will be left with basically volts, just simply volt. So you don't really need to do any sort of conversion over here, and the reason for that is that basically we said that, for example, I2 to I1 is equal to, for example, R1 to R2. Now if you cross multiply, you'll get I2 times R2 is equal to basically R1 times I1, right? So that's basically this relationship. Now if I enter this, if I enter my I of t as 30 milliamps, then of course each of these currents is going to be in milliamps, and then entering each of these resistors in kilo ohms, then the milli and kilo will cancel out, and then you will have no problem there. So again, you don't need to convert anything here. So then, but again, we need to use the relationship I of t is equal to I1 plus I2, because it's a parallel circuit. And so I can write, for example, I of 2 as I of t minus I of 1. So I of 2 is equal to I of t, which is equal to 30 milliamps. 30 milliamps minus I of 1. So I can write I of 2 as 30 minus I1 over I1 is equal to R2 to R1 to R2, which is equal to 12 by 6, which is equal to 2. So 2 times I1 is equal to 30 minus I1. So 2 times I1 plus I1 is equal to 30, and so 3 times I1 is equal to 30, and so I1 is equal to 10, of course, in milliamps. 10 milliamps. And we said that basically I1 plus I2 was equal to I of t, which was equal to 30 milliamps. So it's equal to 30 milliamps. So now I1 was 10 milliamps plus I2 is equal to 30. So I2 is equal to 30 minus 10. So I2 is equal to 20 milliamps. So that's I2. So that is that. And now there is something here that you need to know at least a little bit about, and that is something called basically the Kirchhoff's current law and the Kirchhoff's voltage law. So the KVL and the KCL. This is the Kirchhoff's Kirchhoff's voltage law, and this over here is the Kirchhoff's current law. You need to know about that. And what this means is that, so in the case of, we will talk about these two, and then we will go back to these two, to this, for example, to the circuit that we just solved, and we will see a couple of things about that over there. So so the Kirchhoff's current law basically simply states that the total current entering a junction in a circuit, it says that the total current entering a junction in a circuit must equal the sum of the currents leaving the junction. So the total current entering a junction in a circuit must equal to the sum of the currents leaving the junction. What that means is that basically, for example, let's say that you have this situation over here. You have two basically resistors over here in parallel. You have R1 and R2 over here, and there is some current coming in I of t, which is equal to some I of t. Basically, it doesn't really matter what that is. And then, of course, when I of t gets to this point, it gets divided into I1 and I2. I1 and I2. Now what that means is that now the Kirchhoff's current law states that basically the total current, or I of t, entering a junction in a circuit must equal to the sum of the currents leaving the junction, meaning that basically, for example, at this junction, the total current entering this junction is I of t. The sum of basically all the currents leaving that junction are basically I1 and I2. So that means that over here then I1 plus I2 must be equal to I of t. Again, over here I1 and I2 come to this junction. This is I1 and this is I2. And then I of t basically leaves this junction. Again, the total current entering this junction, which is I1 plus I2, is supposed to be equal to I of t. And that's basically the whole story here. That is the Kirchhoff's current law. There is also the Kirchhoff's voltage law, which is something similar. It says that basically all the voltages basically coming, or basically the algebraic sum of all the voltages entering and leaving a node in a circuit. So for example, you have this circuit over here, you have this resistor and this resistor over here, you have this resistor over here, you have this resistor over here, and you have also this resistor over here, and then this goes to some, for example, power supply. So there is a node over here which is basically for example, let's call it point C, for example, in this circuit. So in this circuit, basically depending if you take this point positive and this point negative, then based on that, some voltages entering this node are going to be positive and having some magnitude, and then again, relative to that, there will be some negative voltages at this node as well, having some magnitude. Taking into consideration the magnitude of those voltages and the algebraic signs, the sum of all of those voltages coming in and coming out is going to be equal to 0. And that's basically the Kirchhoff's voltage law. Now we need to basically go back to the voltage divider circuit that we had at least in the previous example. We had basically this resistor over here and another resistor over here, and I of t coming in was 30 milliamps. And we had 12 kilo ohms as R1. R1 was 12 kilo ohms, and R2 was basically 6 kilo ohms. R2 was 6 kilo ohms. And we calculated some values for I1 and I2, as this is I1 and this is I2. So we calculated I1 as 10 milliamps, and I2 as 20 milliamps. Of course, you can see that basically I1 plus I2 is equal to I of t. That you already have seen over here. Now, there is something important here, and it says that the current through a resistor, so this resistor is a 12 kilo ohm resistor, this resistor is a 6 kilo ohm resistor. The current going through this resistor is 10 milliamps. The current going through this resistor is 20 milliamps. So the value of this resistor is twice the value of this resistor, and the current going through that resistor is half the current going through the other resistor. So again, I repeat this: the value of this resistor is twice the value of this resistor, and the current going through that resistor is half of the current going through the other resistor. So then you can say that the current through a resistor is inversely proportional to the resistor's value. The current through a resistor is inversely proportional to its value. So then you can say that if one resistor is larger than, for example, another in a parallel circuit, the current flowing through the higher value resistor is the smaller of the two, and as you can see here, basically that is the case. If one resistor, this resistor is larger than the other resistor, and the two resistors are connected in parallel, and the current going through the larger resistor is the smaller of the two currents passing through the two resistors. And so that's also something that you can see in this circuit, which is something important. Now we will of course see the same thing we have another example here that we will solve, and we will see the same thing over there as well.